The cosmic distance ladder is the succession of methods by which astronomers determine the distances to celestial objects. A real direct distance measurement of an astronomical object is possible only for those objects that are close enough to Earth. The techniques for determining distances to more distant objects are all based on various measured correlations between methods that work at close distances and methods that work at larger distances. Several methods rely on a standard candle, which is an astronomical object that has a known luminosity. The ladder analogy arises because no single technique can measure distances at all ranges encountered in astronomy. Instead, one method can be used to measure nearby distances, a second can be used to measure nearby to intermediate distances, and so on. Each rung of the ladder provides information that can be used to determine the distances at the next higher rung. Direct measurement. At the base of the ladder are fundamental distance measurements, in which distances are determined directly, with no physical assumptions about the nature of the object in question. The precise measurement of stellar positions is part of the discipline of astrometry. Astronomical unit direct distance measurements are based upon the astronomical unit, which is the distance between the Earth and the Sun. Historically, observations of transits of Venus were crucial in determining the O. In the first half of the 20th century, observations of asteroids were also important. Presently, the orbit of Earth is determined with high precision using radar measurements of distances to Venus and other nearby planets and asteroids, and by tracking interplanetary spacecraft in their orbits around the Sun through the Solar System. Kepler's laws provide precise ratios of the sizes of the orbits of objects orbiting the Sun, but provides no measurement of the overall scale of the orbit system. Radar is used to measure the distance between the orbits of the Earth and of a second body. For that measurement and the ratio of the two orbit sizes, the size of Earth's orbit is calculated. The Earth's orbit is known with a precision of a few meters. Parallax. The most important fundamental distance measurements come from trigonometric parallax. As the Earth orbits the Sun, the position of nearby stars will appear to shift slightly against the more distant background. These shifts are angles in an isosceles triangle, with two astronomical units making the base leg of the triangle and the distance to the star being the long equal-length legs. The amount of shift is quite small, measuring 1 arcsecond for an object at the 1 parsec distance of the nearest stars, and thereafter decreasing in angular amount as the distance increases. Astronomers usually express distances in units of parsecs. Light years are used in popular media, because parallax becomes smaller for a greater stellar distance. Useful distances can be measured only for stars whose parallax is larger than a few times the precision of the measurement. Parallax measurements typically have an accuracy measured in milliseconds. In the 1990s, for example, the Hippocos mission obtained parallaxes for over 100,000 stars with a precision of about a millisecond, providing useful distances for stars out to a few hundred parsecs. The Hubble telescope WFC3 now has the potential to provide a precision of 20 to 40 microarcseconds, enabling reliable distance measurements up to 5,000 parsecs for small numbers of stars. By the early 2020s, the Gaia space mission will provide similarly accurate distances to all moderately bright stars. Stars have a velocity relative to the Sun that causes proper motion and radial velocity. The former is determined by plotting the changing position of the stars over many years, while the latter comes from measuring the Doppler shift the star's spectrum caused by motion along the line of sight. For a group of stars with the same spectral class and a similar magnitude range, a mean parallax can be derived from statistical analysis of the proper motions relative to the radial velocities. This statistical parallax method is useful useful for measuring the distances of bright stars beyond 50 parsecs and giant variable stars, including Cepheids and the Alari variables. The motion of the Sun through space provides a longer baseline that will increase the accuracy of parallax measurements, known as secular parallax. For stars in the Milky Way disk, this corresponds to a mean baseline of 4 astronomical units per year, while for halo stars the baseline is 40 astronomical units per year. After several decades, the baseline can be orders of magnitude greater than the Earth-Sun baseline used for traditional parallax. However, secular parallax introduces a higher level of uncertainty because the relative velocity of observed stars is an additional unknown. When applied to samples of multiple stars, the uncertainty can be reduced. The uncertainty is inversely proportional to the square root of the sample size. Moving cluster parallax is a technique where the motions of individual stars in a nearby star cluster can be used to find the distance to the cluster. Only open clusters are near enough for this technique to be useful. In particular, the distance obtained for the Hyades has historically been an important step in the distance ladder. Other individual objects can have fundamental distance estimates made for them under special circumstances. If the expansion of a gas cloud, like a supernova remnant planetary nebula, can be observed over time, then an expansion parallax distance to that cloud can be estimated. Those measurements, however, suffer from uncertainties in the deviation of the object from sphericity. Binary stars, which are both visual and spectroscopic binaries, also can have the distance estimated by similar means, and don't suffer from the above geometric uncertainty. The common characteristic to these methods is that a measurement of angular motion is combined with a measurement of the absolute velocity. The distance estimate comes from computing how far the object must be to make its observed absolute velocity appear with the observed angular motion. Expansion parallaxes in particular can give fundamental distance estimates for objects that are very far, because supernova ejecta have large expansion velocities and large sizes. Further, they can be observed with radio interferometers, which can measure very small angular motions. These combine to provide fundamental distance estimates to supernovae in other galaxies. Though valuable, such cases are quite rare, so they serve as important consistency checks on the distance ladder rather than workhorse steps by themselves. Standard ruler. Another class of physical distance indicator is the standard ruler. In 2008, galaxy diameters have been proposed as a possible standard ruler for cosmological parameter determination. The method exploits regularity in baryon acoustic oscillations in the early universe. While small structures occur at all scales, acoustic oscillations in the primordial plasma did not exceed a certain length. The inhomogeneities in the plasma were then organized by gravity into galaxy filaments and voids. Consequently, cosmic voids are not expected to exceed a maximum size determined by the size of the BAOs that gave rise to them. The method requires an extensive galaxy survey in order to make this scale visible. The Wiggles galaxy survey was able to resolve this scale for detecting the expansion effect of dark energy. Light echoes can be also used as standard rulers. Galactic distance indicators. With few exceptions, distances based on direct measurements are available only out to about 1,000 parsecs, which is a modest portion of our own galaxy. For distances beyond that, measures depend upon physical assumptions, that is, the assertion that one recognizes the object in question, and the class of objects is homogeneous enough that its members can be used for meaningful meaningful estimation of distance. Physical distance indicators used on progressively larger distance scales include dynamical parallax, uses orbital parameters of visual binaries to measure the mass of the system, and hence use the mass-luminosity relation to determine the luminosity eclipsing binaries. In the last decade, measurement of eclipsing binaries' fundamental parameters has become possible with 8-meter-class telescopes. This makes it feasible to use them as indicators of distance. Recently, they have been used to give direct distance estimates to the Large Magellanic Cloud, Small Magellanic Cloud, Andromeda Galaxy and Triangulum Galaxy. Eclipsing binaries offer a direct method to gauge the distance to galaxies to a new improved 5% level of accuracy, which is feasible with current technology to a distance of around 3 mpc. Are variables used for measuring distances within the galaxy and in nearby globular clusters. The following 4 indicators all use stars in the old stellar populations: tip of the red giant branch distance indicator, planetary nebula luminosity function, globular cluster luminosity function, surface brightness fluctuation. In galactic astronomy, X-ray bursts are used as standard candles. Observations of X-ray bursts sometimes show X-ray spectra indicating radius expansion. Therefore, the X-ray flux at the peak of the burst should correspond to Eddington luminosity, which can be calculated once the mass of the neutron star is known. This method allows distance determination of some low-mass X-ray binaries. Low-mass X-ray binaries are very faint in the optical, making the distances extremely difficult to determine. Interstellar masers can be used to derive distances to galactic and some extragalactic objects that have maser emission. Cepheids and novae, individual galaxies in clusters of galaxies. The Tully-Fisher relation, the Faber-Jackson relation, type Iowa supernovae that have a very well-determined maximum absolute magnitude as a function of the shape of the light curve and are useful in determining extragalactic distances up to a few hundred mpc. A notable exception is SN 2003 FG, the Champagne supernova, a type Iowa supernova of unusual nature. Redshifts and Hubble's law, main sequence fitting. When the absolute magnitude for a group of stars is plotted against the spectral classification of the star in a Hertzsprung-Russell diagram, evolutionary patterns are found that relate to the mass, age and composition of the star. In particular, during the hydrogen burning period, stars lie along a curve in the diagram called the main sequence. By measuring these properties from a star's spectrum, the position of a main sequence star on the HR diagram can be determined, and thereby the star's absolute magnitude estimated. A comparison of this value with the apparent magnitude allows the approximate distance to be determined. After correcting for interstellar extinction of the luminosity because of gas and dust, in a gravitationally bound star cluster such as the Hyades, the stars formed at approximately the same age and lie at the same distance. This allows relatively accurate main sequence fitting, providing both age and distance determination. Overlap and scaling. A succession of distance indicators, which is the distance ladder, is needed for determining distances to other galaxies. The reason is that objects bright enough to be recognized and measured at such distances are so rare that few or none are present nearby. So there are too few examples close enough with reliable trigonometric parallax to calibrate the indicator. For example, Cepheid variables, one of the best indicators for nearby spiral galaxies, cannot yet be satisfactorily calibrated by parallax alone. The situation is further complicated by the fact that different stellar populations generally do not have all types of stars in them. Cepheids in particular are massive stars with short lifetimes, so they will only be found in places where stars have very recently been formed. Consequently, because Because elliptical galaxies usually have long ceased to have large-scale star formation, they will not have Cepheids. Instead, distance indicators whose origins are in an older stellar population must be used. However, R'Lyre variables are less luminous than Cepheids. A novae are unpredictable, and an intensive monitoring program, and luck during the program, is needed to gather enough novae in the target galaxy for a good distance estimate, because the more distant steps of the cosmic distance ladder depend upon the nearer ones. The more distant steps include the effects of errors in the nearer steps, both systematic and statistical ones. The result of these propagating errors means that distances in astronomy are rarely known to the same level of precision as measurements in the other sciences, and that the precision necessarily is poorer for more distant types of object. Another concern, especially for the very brightest standard candles, is their standardness, how homogeneous the objects are in their true absolute magnitude. For some of these different standard candles, the homogeneity is based on theories about the formation and evolution of stars and galaxies, and is thus also subject to uncertainties in those aspects. For the most luminous of distance indicators, the type Iowa supernovae, this homogeneity is known to be poor. However, no other class of object is bright enough to be detected at such large distances, so the class is useful simply because there is no real alternative. The observational result of Hubble's law, the proportional relationship between distance and the speed with which a galaxy is moving away from us, is a product of the cosmic distance ladder. Hubble observed that fainter galaxies are more red-shifted. Finding the value of the Hubble constant was the result of decades of work by many astronomers, both in amassing the measurements of galaxy redshifts and in calibrating the steps of the distance ladder. Hubble's law is the primary means we have for estimating the distances of quasars and distant galaxies in which individual distance indicators cannot be seen. Bibliography: An Introduction to Modern Astrophysics, Carroll and Osley, copyright 2007. Measuring the Universe, the Cosmological Distance Ladder, Stephen Webb, copyright 2001. Pasachov, J.M. and Amp, Filipenko A.V., The Cosmos, Astronomy in the New Millennium, Cambridge, Cambridge University Press, 4th edition, 2013, ISBN 9781107687561. The Astrophysical Journal. The globular cluster luminosity function as a distance indicator. Dynamical Effects. Ostraker and Needham, May 5, 1997. An Introduction to Distance Measurement in Astronomy. Richard de Grigis, Chichester, John Wiley and Amp Sons, 2011. ISBN 9780470511800.